All right, let's finish up problem 4. All right, so we'd already figured out when the temperature of the neutron star is 10 to the 5th, we get something that's much less than the luminosity of the sun, in particularly 1.8 times 10 to the minus 5th. Then notice when the temperature jumps up to 10 to the 7th, right? It's the same equation, but now we have 10 to the 7th. Remember, you're raising it to the 4th power, so you get an much greater temperature. And then again, the last one, part C, they want you to find the luminosity of this neutron star compared to when the surface temperature is 10 to the 9th. So this is what it looks like. All right, so let's see. Let me put the numbers in that I get. So the one for when the temperature is 10 to the 7th, I get 1,822 times the luminosity of our sun. That's an S. All right. When it's 10 to the 9th, when the surface temperature is 10 to the 9th, it's enormous, right? So this becomes 1.8 times 10 to the 11th, right? Times the luminosity of our sun. Okay, and I think they asked us as well, could you plot this on the HR diagram? This one you could plot on the HR diagram. This one you could plot on the HR diagram. This one it wouldn't fit. This one would, the last one, part C, would just the HR diagram. The normal one that we look at does not have something. This is just a little less than a trillion times the luminosity of the sun. So no, that one would not fit on our standard HR diagram. All right, let's look at the next problem, which I think is number 6. Here, let's set that up here. So this is number 6. Looks like we're doing the Schwarzschild radius. Let me go through the Schwarzschild. I'll read the question in just a second. So I mentioned this in class, but I want to make sure everybody sees this. So just as a reminder, the escape velocity, Isaac Newton came up with this formula 350 years ago, is equal to the square root of 2 times big G times the mass of the object divided by the radius of the object. And so it's the square root of all that. All right, so this guy Schwarzschild, that's how you pronounce his name, Schwarzschild, he said, what if we let the escape speed, what if we let this be the speed of light? So let's set that equal to the speed of light. So this is really what his contribution was. And so if we set the escape speed equal to the speed of light, of course you're talking about a black hole. Now he did this work back in right around World War I. So this was really shortly after the time Einstein was or might have been during the time Einstein was publishing the general theory of relativity. Anyhow, if you rearrange this equation, and so what I have in the box, and solve for r, that's what's called the Schwarzschild radius. All right, so let's do that. Here was his great contribution. Square both sides of the equation, you get 2gm over r, and I'm gonna now make it a capital R, and I'm gonna call it r Schwarz, and that's equal to, notice this, I had to square both sides, so that's equal to the speed of light squared. And then really it's just one more step where you bring r over to the left hand side, and then the c squared over to the other side, and so this is what r Schwarz, the Schwarzschild radius, looks like. So it's equal to 2 times big G, again that's just a constant, times the mass of the object divided by the speed of light squared. So this equation right here, this is the one that we're interested in. So basically it tells you the size something is going to be for it to be a black hole. So R is the distance from the center. The center of a black hole, by the way, is called the singularity, and the edge here, right where the escape speed becomes the speed of light, that's called the event horizon. So that part right here is the event horizon. Event horizon. All right. Horizon. And so this is, and what's nice about this is you're not using any equations in general relativity, which tend to be very, very complicated. And the other thing is, the only thing that's the variable here is the mass. The mass is the only variable. So really, you could take any mass and calculate what the Schwarzschild radius is. Now the problem is, for objects like a human being or a building or the entire planet Earth, there is no mechanism for something the size of the planet Earth or even the planet Jupiter to turn into a black hole. Even something the mass of the sun is never going to become a black hole. It's only when you have something that is 3 times the mass of the sun, after it's had to have started its life as a much, much more massive star, probably 25 times the mass of the sun or greater. After the supernova explosion, if there's 3 times the mass of the sun remaining, this supernova remnant, that then not even neutron degeneracy pressure can hold it up, and it will crush in on itself, and in the outer part of it, or a distance of R Schwarz from the center that's where the escape speed's going to become the speed of light. So that's the only actual mechanism for that to happen. All right, so let's do some of these problems. Let's see. So they want us to know, what would be the Schwarzschild radius of something. Well, all right. So now that we're armed with the equations of the equation of the Schwarzschild radius, here's what it says: a supermassive black holes are thought to exist at the centers of most galaxies. In fact, we've been verifying that for many years. Anyhow, what is the Schwarzschild radii of the black holes of 1 million and 1 billion solar masses, respectively? How does the 1 million solar mass compare in size with the sun, and how does the 1 billion solar mass compare with the size of the solar system, compared to the size of the solar system? All right, so we're going to do this. Keep in mind that the Schwarzschild radius comes out in units of meters. So we'll do. So here I've already set it up right here. So this is the one for 1 million times the mass of the sun. So this would be, like, for example, just to, it's not this problem, but the one at the center of our galaxy, the Milky Way, is about 4 million times the mass of the sun. All right, so anyhow, there's the Schwarzschild radius. It's just 2 times big G, and then the mass is the only variable, right? So there's 1 million, 10 to the 6 times the mass of the sun, and remember, it's divided by the speed of light, which is 3 times 10 to the 8th meters per second, and you got to square that. Anyhow, when we do that, here is the Schwarzschild radius. It comes out to be, let's see, what is it? It's about 2.96 times 10 to the 9th. 10 to the 9th. Meters. All right. All right, just to give you some sense, we're going to compare that to the size of the sun. So this is the Schwarzschild radius. If you compare it to the size of the sun is 696,340 kilometers, or to change that to meters, it's times 10 to the 3rd, or just add 3 zeros, meters, right? And so that tells us. So this is this is the number. Of course, the numerator is bigger, so this thing turns out to be 4.3 times the radius of our sun. All right, so in other words, the Schwarzschild radius of something that is 1,000,000 times the mass of the sun. All right, that'll definitely crush down to a black hole. The black hole would be 4.3 times the size of our sun. All right, let's do the one for 1,000,000,000. Again, it's the same thing. So you basically do the exact same equation, but instead of 10 to the 6, you just put a 10 to the 9th right there. All right, so here we'll do it here. All right, so this is part B. How much time do I have? Yeah, I got time. So part B. Let's see. So this is the Schwarzschild radius. Schwarzschild of the billion one. Again, it's just 2 times 6.67 times 10. That's supposed to be a 7 times 10 to the minus 11th. Right. That's the universal gravitational constant, never changes, and then times a billion, which is just 10 to the 9th, times the mass of the sun, which is. So we're multiplying by 2 times 10 to the 30th. That's supposed to be a 30th. And then you divide by the speed of light squared. So it's, of course, 3 times 10 to the 8th. 3 times 10 to the 8th. But we have to square that, right? All right, and so this comes out to be, let's see. So this comes out to be 2.9 times 10 to the 12th times 10 to the 12th meters. All right, and so what we would do is, I think a natural thing to do for this is to turn this into astronomical units. Okay, so here's what we're going to do. It turns out that there's 1.5. So this is the distance from the Earth to the Sun, by the way, 1.5 times 10 to the 11th meters. All right, that's called an astronomical unit. Okay, we've used that many times. Anyhow, see, the number in the numerator is a little bit bigger. Well, we're figuring out exactly how much bigger it is, and it turns out that this is just under 20 astronomical units. So it turns out to be 19.8 astronomical units. All right, so I think, yeah, that takes us out beyond the orbit of Saturn, for example. So if this was, if this black hole, this is a billion times the mass of the sun, black hole, it would extend out beyond the orbit of Saturn, taking up a large fraction of the solar system. The solar system is probably, I don't know, maybe 100, we don't know exactly how big the solar system is, but everything that we can see is in around about 100 astronomical units out. Those are, things well beyond the orbit of Neptune, which is the last planet, of course. The objects I'm talking about that are out about 100 astronomical units are called Kuiper Belt objects. All right, so let's see, what's the next problem? No, number 7. All right, let's actually just look at number 7 real quick, and I'll read it. All right, so in the information, so we're going to use this deflection. This is actually an equation that comes from Einstein's theory of general relativity, and so we'll see the angle theta. Basically, how much is light bent by a massive object? Okay, so Einstein actually calculated this, and so the different objects we're going to use is the light beam going by the moon, not hardly bent at all, by Jupiter. You can actually see that's something that could bend significantly, by the star Sirius B, which, remember, is a white dwarf around the brightest star in the night sky. Sirius A. Anyhow, Sirius B is actually quite massive, and it's really tiny, so it's really warping the space-time around it,